molar mass. We often need to know the number of atoms in a sample. So we can weigh a sample out, maybe it's 10 grams, but we need some indication of the number of atoms in the sample. And the reason for that is because chemical processes happen between particles. When you make water, you have one oxygen and two hydrogens. And it's always 2 to 1. And so the numbers of particles then become important because they combine in whole number ratios of numbers of particles. But the number of particles ends up being this ginormous number, and it's just way too big to deal with. Let's pretend you're building a fence for your backyard, and you go to the hardware store, and you made some plans for this fence, and you find out that you need 2,400 nails to make this fence. Are you going to stand there and count out 2,400 nails? That's going to be tedious. And the guy who checks you out is not going to want to count and check that you counted correctly. No, they've got a big old scoop and they've got a scale. And the nails are listed. This is, 50 per pound or 10 per pound or whatever, depending on the size of the nail. So you figure out the mass of nails and the number per pound, and then you can count them by weighing them. We do this a lot in everyday life without even really realizing it. And so we're going to do the same thing with atoms. We can count them by weighing them, which is good because they're way too small to count. When we count large numbers of objects, we often use counting units. We all know what a dozen is, right? A dozen is 12. You could have a dozen eggs. You could have a dozen donuts. You could have a dozen spaceships. You could have a dozen planets. You could have a dozen anything. It's just 12 of them. There's another unit you might not be as familiar with, a gross. A gross is a dozen. So 144 objects. Another counting unit is the ream. A ream of paper means there's 500 pieces. In chemistry, we have our own counting unit because 12 and even 144 or 500, way too small to be useful. So we call this the mole. We often refer to it as the chemist's dozen. And this is a concept that's sometimes hard for students to get through their mind. What the heck is this mole thing? It's not a small furry animal. It's not a sauce. We're not talking mole here. It's just mole. And it's abbreviated MOL. A mole is the amount of stuff that has 6.02214 times 10 to the 23rd particles. That's a big, big number. I think I need to refresh my memory on these analogies. I think if you had 6 times 10 to the 23rd marbles, it would occupy the volume of the moon. That's a lot of marbles, right? A 6 with 23 zeros after it. It's just huge. It's a really useful number in chemistry, though. So we need to remember that 1 mole is 6.022 times 10 to the 23rd particles. It is known to more significant digits. Most of the time we just use the first 4. And that number has a name. It's called Avogadro's number in honor of the man whose work led to the discovery of this quantity. So a mole can specify Avogadro's number of anything, just like a dozen means 12 anything. You can have a mole of marbles. You can have a mole of sand grains, 6.022 times 10 to the 23rd sand grains. If you took 1 grain of sand, just to give you an idea of how small atoms are, if you took 1 grain of sand and figured out the number of atoms in it and made each of those atoms the same size as the grain of sand, it would be about the size of Mount Everest. That's how small they are. Yes, question?
Does a mole, does that have any special significance, like as a specific, I don't know, any specific significance, or is that just the number that they made?
It does have significance, and it has to do with that definition of the atomic mass unit, which is right here.
I see.
Yeah. So how did we get that number? Did they just pull it out of the air? No. The value of the mole equals the number of atoms in exactly 12 grams of pure carbon-12. So carbon-12 is the isotope of carbon that has 6 protons, 6 neutrons. Okay, and so by definition of the units, it weighs exactly 12 atomic mass units. And so what they did is they said, well, if we have 12 grams of carbon-12, how many atoms would there be? That turns out to be Avogadro's number. When we define things like that, then 1 mole of carbon atoms weighs 12 grams, but 1 atom weighs 12 atomic mass units. So 1 atom of carbon-12 weighs 12 atomic mass units. So because of the way the mole is defined, the mass of an atom in atomic mass units is the same number as the mass of 1 mole in grams. And so the numbers on the periodic table, let's look at, I don't know, chlorine, 35.453. That means that 1 atom weighs 35.453 atomic mass units. 1 mole of chlorine weighs 35.453 grams. And so that's how it gets its value.
So would 1 mass unit be a proton, the weight of a proton and a neutron?
Yes, one proton weighs approximately 1 atomic mass unit. It's not exactly, but it's close. 1 neutron is also 1 atomic mass unit. So they're about the same. Any other questions? Oh, I should. So we have this relationship then, 12 grams of carbon equals 1 mole of carbon, and that equals Avogadro's number of atoms. So we can convert between moles and number of atoms just like we convert between dozens and numbers of eggs. For moles, for atoms, you're going to use this relationship. 1 mole is equal to Avogadro's number, instead of 1 dozen equals 12 eggs. You can make this equivalence into 2 different conversion factors, and which one you use just depends on whether you're going from atoms to moles or the other way around. And dimensional analysis will take care of the question, do I multiply or do I divide? You look at the units and do whatever's needed for the units to work out. Let's do an example. A pure silver ring contains 2.80 times 10 to the 22 silver atoms. How many moles of silver atoms does it contain? Read the problem all the way through, find the numbers, and identify what those are. So 2.80 times 10 to the 22 silver atoms. There's only 1 number in the problem, so that's probably the number we're going to convert into something else. What's the question? How many moles? So I need to go from atoms to moles of silver. And we can do that in 1 step. The relationship is that 1 mole equals 6.022 times 10 to the 23rd atoms. Sometimes it'll be ions, sometimes it'll be molecules. It's just a number, a counting number. So I'm going to use dimensional analysis to figure this out. 2.80 times 10 to the 22 atoms I'm converting to moles. I want moles on top. I want atoms on the bottom so that the units work out. That tells me where to put the number. 1 mole, the funny mooing sound is the balances. They just do that. They're like adjusting themselves. And it sounds like a cow. 6.022. See, I told you I was distractible. 6.022 times 10 to the 23rd atoms. If you get confused and aren't sure, does that number go with moles or atoms? Think about eggs. 1 dozen equals 12 eggs. You wouldn't say that 12 dozen equals 1 egg, because that would be silly. The mole is the chemist's dozen. Now we need to do this on our calculators, and this is why you have to have a scientific calculator and you have to understand scientific notation, because I've never seen a pocket calculator that will let you put in Avogadro's number in decimal form. And who would want to count the number of zeros anyway? So get your calculator out and make sure that you're getting the right number with me, and if you're not, then during lab I will talk to your calculator and straighten it out for you. So what I'm doing is I'm doing 2.80 EE22 divided by 6.022 EE23, and I'm coming up with 0.0464. 0.0464 96181. And the unit would be mole. Yes?
Can you say that one more time?
So the keystrokes would be 2.80 EE, or it might be EXP on your calculator, 22, divided by 6.022 EE23. There's no times 10 to that in there. The EE button stands for times 10 to that. So if you're miscommunicating with your calculator, you're going to end up with a really, really big number instead of this number that's less than 1. What about sig figs? 3. So our starting number had 3. Now, that's a number of objects, isn't it? Would that be exact? It's counting, isn't it? Oh, but did we really count it? 2 times 10 to the 22? Personally, I knit, and sometimes I have to count like to 200 stitches, and I get distracted and I lose count, right? And you could make some mistakes in there. If you're counting to 2 times 10 to the 22, well, for one thing, it would take you the rest of your life to count that. But when you take it to extremes, counting numbers are not exact. Like if you tried to count the number of people in Fresno, it's up close to 500,000. If one person was counting them, by the time you finish counting, some people will have died, some people will have been born, and the number has changed. And so when you take it to extremes, counting is not exact. 3 sig figs then. Avogadro's number is not exact. As we used it here, it has 4. And so we're going to round this number to 3 sig figs and say it's 0.0465 moles. You can have less than 1 mole of substance, just like you can have less than 1 dozen. You could have half a dozen, right? Any questions? Yes?
Would you be wanting us to write down the element you want us to calculate?
Do I want you to write down the element? Because I wrote the element symbol here, and I didn't down here. At this point, it's not critical. Later, when we're doing this in terms of chemical reactions, then it does become very important, because we're dealing with atoms or molecules of 2 different substances. Good question. Yes?
Stupid question maybe, but you don't want that in scientific form, do you?
We could write it in scientific form. Either would be acceptable. So in scientific notation, it would be 4.65 times 10 to the minus 2. My opinion is that scientific notation is always fine. My rule of thumb is if I have to get my finger out to count the zeros, then I should put it in scientific notation. So if there's like 2 or 3 zeros, we're okay. More than that, scientific notation is better. Any other questions? Well, we need one other thing if we're going to count atoms by weighing them. We've got this unit now, moles. but it doesn't take into account the mass. So molar mass. Atomic mass was the mass of an atom. Molar mass is the mass of a mole of atoms. And I talked about this a little bit earlier. An element's molar mass in grams per mole is equivalent numerically to its atomic mass in atomic mass units. So the number on the periodic table that's under the chemical symbol works for atoms or for moles of atoms. You just change the unit, atomic mass unit or gram. Here we have illustrations of aluminum, carbon, and helium. Helium atoms are smaller than aluminum atoms. 1 mole of aluminum atoms is Avogadro's number of aluminum atoms. It's going to weigh 26.98 grams. 1 mole of carbon is Avogadro's number of carbon atoms. But the carbon atoms are smaller. So if we have the same number of them, they're going to weigh less. That should make sense. If you take a full-size luxury sedan and you have 12 of those, and you compare the mass of those 12 luxury cars to 12 subcompact cars, which dozen cars is going to weigh more? The luxury sedans, the big car, 12 of them. Yeah, you have 12 of each, but the little cars weigh less. So here we have the subcompact version of an element, helium. Same number of helium atoms is going to weigh less. So the lighter the atom is, the less mass there is for 1 mole of atoms. To convert between mass and moles, we use the molar mass. So 12 grams of carbon is equal to 1 mole of carbon, 12.01. This number is from the periodic table. We can make 2 conversion factors out of that, 12 grams per mole or 1 mole per 12 grams. And which one you use just depends on the direction of the conversion that you're doing. Let's do an example. Calculate the amount of copper in moles in a 35.8 gram pure copper sheet. We read the words, we find the numbers, and write them down. 35.8 grams. Now, we do need to know which element this is. It's copper. And they're asking us to find the amount in moles. So they're giving us grams, and they're wanting us to find moles of copper. Do we have a relationship that allows us to go directly between grams and moles? Yeah, it's the molar mass. 62.5?
No, 63.55.
Yeah, that sounds better. 63.55. So we look it up in the periodic table. 63.55 grams of copper is equal to 1 mole of copper. So I'm going to go from grams to moles. I have 1 arrow. I have 1 conversion factor, 35.8 grams of copper. And I'm going to moles of copper. And I want grams of copper in the denominator, so the units work out. 1 mole weighs this much. 1 mole and 65.88 is with the grams. So I don't have to think about, do I multiply by that or divide? The units tell me. 35.8 divided by 63.55. My calculator tells me 0.5633359